Okay, we are going to take a look at a really helpful framework for looking at modern design challenges called systems thinking. And to do that, it's helpful to look at some of the ways that design has changed over time since its inception. So, design is changing in the ways that it has moved from where it started in the industrial age into what is now the information age. Design has changed from something that was just a service to something that is authorship in its own right and is responsible for the things that it creates. We've moved from creating static things into dynamic systems. So, being responsible for softwares and applications and things that move and change. We've stopped creating just objects and we've started creating tools. So, you can think about this like we no longer just design posters in Photoshop, but designers are actually designing Photoshop so that more people can do design work. Designers have stopped being the experts on the things that they work on, and they are now participants that are helping lead those discussions. And we're shifting from human centered design, so just thinking about the user, to humanity centered design, where we're thinking about all the different aspects that might influence the systems that we're working on. And finally, design solutions have turned into design responses, which we'll talk a little bit more about. So, as the tools of formal production continue to be democratized, so it becomes easier and easier to create through tools like Adobe, tools like Canva, nowadays generative AI. That's a good thing because it means that more people can produce design artifacts, but it also means that the economic value of design is more than ever shifting from just being able to make those things to the other parts of the design process, like research, being able to empathize with users, understanding the problems, imagining solutions, and synthesizing the information that comes from all of those things to creating the correct response, not just the technical ability to make a response. And this leads us into thinking about tame and wicked problems, which you may have heard in other disciplines. This isn't design specific, but it's really helpful for thinking about the modern things that we are dealing with as designers as we are in other disciplines. So we can take a look at some examples to think about what are the differences between tame and wicked problems and what makes these things so difficult for us to solve. So things that we haven't been able to crack yet, things like affordable housing, ethical AI development, integration, and use, declining civic and social engagement or decreasing social connections, how we balance the positive and negative impacts of social media, and how we might reduce polarization when political divisions are increasingly not just about how we respond to societal problems, but those divides are drawn along personal and cultural values. These are all examples of wicked problems. These are problems that lack clarity in their aims and solutions, and they're subject to real world constraints that prevent multiple and risk free attempts at solving. And this is the Stony Brook University definition of this, which I like because it speaks to the way that attempting to intervene in these problems influences the state of them. So, a few definitions here from the original writing on it are that wicked problems don't have a definitive formulation. They don't have a stopping rule, so they continue. Solutions are not true or false. There's no way to test and reverse solutions. Once you try something, it has to be put out into the world. They can't be studied through trial and error. There's no end to the number of solutions or approaches. They are all unique problems. They can be described as symptoms of other problems, so they're connected. The way that you describe them determines the possible solutions. So, depending on how you look at it, can frame what the problem is in the first place. And those who present solutions to the problems have no right to be wrong because of the scale of the impact. And this is a little bit lengthy, but it kind of like puts it in perspective the types of things that we're looking at here. Wicked problems don't have definite solutions, only ongoing responses that are more or less appropriate. And this ties back to some of the ways that we're seeing design challenges change in that we're not designing solutions, we're just designing responses that we need to put into place, see what it does to the problem we're looking at, and then respond again accordingly. Here, I'll flip back to my favorite chart from the Royal College of Art. Looking at the design column here, we can see that one of the things that design is concerned with is practicality, ingenuity, empathy, and concern for appropriateness. So, unlike science, where there is a definitive truth that the discipline is looking for, design is concerned with what is an appropriate response, or not what is perfect, but what is the right thing to do in this situation. And this is exactly the path that gives us agency in something like a wicked problem. And one of the tools that we have to look at this comes from systems thinking. This framework has come from a variety of disciplines. And when I came across it, it was really influential in kind of putting the world in perspective or putting a model around a lot of the things that I was seeing in my work and in life that I found very difficult to explain. And things that were complex, and systems thinking really put a framework around how to describe and think about those things. So, complex problems, often things you will work on in design, require interdisciplinary teams to respond to them, meaning it can't just be designers working on them. And systems thinking has evolved from a lot of interdisciplinary teams, including business management, ecology, computer engineering, economics, and more. People from all different walks of life working on these big picture ideas or societal problems and trying to put some sort of framework around how do we look at these things and address them. I'll get to an example in a minute, but a system is an interconnected set of elements that is coherently organized in a way that achieves something. Now, that thing that it achieves might not be what you intend it to achieve, but it does systematically work towards some sort of end goal. And it's made up of elements, interconnections, and whatever that goal is of the system. And this definition comes from Donella Meadows, who wrote a really good introduction to this called Thinking in Systems, which we'll reference a lot throughout this presentation. Some of the principles of systems thinking come from those three elements. The principles are interconnection, causality, and wholeness. And this aligns really closely with another model that we've looked at in design, which is human centered design. These principles from the Interaction Design Foundation of being people centered, solving the right problem in a complex thing, seeing everything as a system, and looking at small and simple interventions. And that word interventions is another synonym for response. So it's not a solution, it's just a way that we're trying to influence the thing that we're working on. So there's a lot of different ways to diagram this and model it, but the one I'm going to use in this presentation comes from Donella Meadows in that original introduction to systems thinking. And she looks at this in terms of stocks and flows. And the way that those things are depicted in these diagrams is any flow is depicted by a valve, and any stock is depicted by a rectangular box. And then the endpoints are always depicted as these clouds because we'll get to it later talking about bounded rationality. But because systems are so connected to everything else, we have to have a cutoff of where we're looking at it. But the clouds sort of recognize that this moves beyond what we're looking at. We're just choosing to zoom in on this aspect. So as an example, we can look at something like a bathtub as a system. And a bathtub, the stock in it, the thing that is measured or quantified, is the level of water in the tub. So that's our stock, and it has inflows and outflows. So one of the things that influences that stock level of water in the tub is the faucet. If we open the faucet more, we get more water. If we close it, we get less water. But there's also an outflow, which is the drain. In both of those, the inflows and the outflows influence what this measurement of water in the tub is. So even if we have the same flow from the faucet, decreasing the size of the drain will mean that the level of water in the tub increases if it's leaving the tub less quickly than it's entering. If that drain is larger and the faucet remains the same, then the level of water in the tub will go down, even though we're still adding water to the tub. And this is a core principle of systems thinking and thinking about the flow of something through the system, not necessarily just the quantity of it. Now, this gets more complex when we start to think about how these flows influence each other. So, once we close one of these diagrams so that it's circular, we get something called a feedback loop. And a feedback loop is a closed chain of causal connections in a system. A good example of this is something like a thermostat. So, if we look at the room temperature, the things that influence that room temperature are the inflow of heat from the furnace, and then the outflow would be heat to the outside. Now, the things that could influence the stock in this system from the outflow side might be the difference between the inside and outside temperatures. Let's say our thermostat or our room temperature is 65 degrees. If it's 65 degrees outside, there will be no heat that leaves this room. And so this outflow will be essentially zero. Now, if the outside temperature is zero, the room temperature will cool much more quickly. And so, this discrepancy between the room temperature and the heat outside is something that influences this flow. So, it's sort of self regulating. If this temperature outside is colder, the heat leaves the room more quickly. If it is warmer, then the room temperature is also influenced in terms of the rate of that flow. So, this is what we call a balancing loop, in that the flows here are always trying to reach an equilibrium between the outside temperature and the temperature in the room. Now, of course, we don't want the temperature in the room to be zero. So, we set our thermostat to be something much warmer than that. And that influences how much heat is coming from the furnace or how often the furnace is running. So, the discrepancy between the thermostat setting and the desired or the room temperature and the desired temperature, which is represented by the thermostat setting, influences the flow of heat from the furnace. And so this is also a balancing loop, trying to reach an equilibrium between the room temperature and the thermostat setting. So in this simple system, we have two balancing loops. And both of these are competing against each other to pull the room temperature, the stock of heat in the room, in both directions. And so we can ask ourselves what happens when one of these is more powerful than the other. Now, there's another type of feedback loop, and we can look at another example to see this. So, in this system, we're looking at the population of a society as the stock, and then the inflow would be births, and then the outflow would be deaths. And the thing that influences those deaths is the mortality rate. So, the more people there are in the population, the more deaths there are. And so, this stock itself influences its own system because obviously you need population to pass away, which is the thing that turns this valve on the death's flow. And so, these things are always trying to reach equilibrium. But the input here is births, and this is a different type of feedback loop. This is a reinforcing loop. So the more people there are in the population, the more births you have. And so if this ran unchecked, we would simply have more and more and more people. If the balancing loop were greater than the reinforcing loop, this population would decline in stock. And so a lot of what we're looking at in systems is not necessarily what are the feedback loops, but what is the dynamic between the strength of those feedback loops. So how do we know what to put in these system maps to look at a system? Well, it's not a perfect science. It depends a lot on how you look at the problem. So thinking back to those principles of wicked problems. But a lot of it comes from our human-centered design research, our literature reviews, and our conceptual frameworks of those problems, which is why the system maps look so similar to concept maps, which we've looked at in the past. Another tool we can use to decide what goes into these system maps is the iceberg model, which is really similar to that 5 whys analysis. So we look at an event, we say, okay, what just happened? What is the thing that I want to react to? In this example, it's catching a cold. We look at what is the underlying pattern and trend of that event. So, what has happened in the past. So, in this example, it is that I've been catching more colds when sleeping less. And then saying, okay, what are the underlying structures that influence that pattern? In this case, more stress at work, not eating well, difficulty accessing healthy food near home or work are all things that are influencing the level above it. And then finally, we can look at the mental models that are underneath those structures. So, what are the assumptions or beliefs that are causing those structures to be in place, which influence the patterns, which influence the events? In this example, it is the belief that career is the most important piece of our identity, healthy food is too expensive, and rest is for the unmotivated. And so, one way that we can impact these top level events is by addressing or trying to address these underlying mental models, or really any of these steps in between. Now, these are simple examples. They get much more complex when you're looking at a real world system. So, this is an example from the System Mapping Academy, which you obviously can't see on this slide. But zooming in, they are looking at the system of fast fashion. And this is just one area looking at the consumer behavior within that network or within that system of events. So I won't go through this in this video just for time's sake. This is a really good example if you're looking for a real world system map. So, in summary, the things that we need to know about systems is that they are made up of nodes, which are the things in the system. These can be the actors, products, policies, messages, or events. There are connections between those nodes, and those are the relationships. The connections are what influence the flows, and that's the direction of influence. So, the movement of material, information, or value. And then those flows also have polarity. So, when one goes up, does the connected stock go up, or does it move in the opposite direction? Feedback loops are closed chains of causal connections. And then boundaries are the ends of where we're choosing to analyze those things.